In this video, we'll be discussing the method of initial rates. By now we're familiar with the concept that as a reaction proceeds, the concentration of a reactant or the reactants will go down. And as the concentration of a reactant goes down, the speed of the reaction decreases. Now the rate of reaction is what is of most interest to us right now. Now the simplest form of the rate of reaction is just the average rate of reaction. For that we would just take the change in concentration or the decrease in concentration over time. But this doesn't give us a very accurate view of the rate of the reaction. The other method is the instantaneous rate of reaction. Here we'll take a look at the tangent on the line at different points, and again this will tell us the rate of reaction at that point, but what we really want to know is what is the rate of reaction at any one time. And that's something we're leading up to. Now the concept of the initial rate, well that's just the instantaneous rate at the very beginning of the reaction, or time zero. So why do we need to know what the initial rate is? Well, what we really want to know is, what is the rate law? The rate law is an equation that relates the rate of reaction to the concentration of reactants. So here we have a very generic reaction. A plus B goes to C and D. The rate of reaction is only dependent on the reactants, and it's relative to the rate constant, which happens to be temperature dependent. So we mention that because we have to run all of our reactions at the same temperature if we want to maintain consistency at this point. Now you notice we have these exponents on the concentrations of A and B. These are the orders of reaction with respect to each one of those reactants. And if you add those exponents, well that's the overall reaction order. Now if we take a generic reaction, or actually let's take this reaction, the decomposition of hydrogen peroxide, we might be tempted to write the rate law is the rate of the reaction is equal to the rate constant times the concentration of hydrogen peroxide, the only reactant, raised to the power of 2. But this is categorically wrong. The exponent on the order of the reaction is not the stoichiometric coefficient. So here I'm using x. The order of reaction must be determined experimentally. It has almost nothing to do with the stoichiometric coefficient. And this is where the method of initial rates comes in. So here we have the reaction of fluorine gas with chlorine dioxide to form chloryl fluoride. Well, here we've been given a lot of useful data. We have 3 experiments. Now you notice something about these experiments. Why are we doing this? Well, what we really want to do is find out what is the order of reaction, the exponent, next to the concentration of each one of these reactants, for fluorine and chlorine dioxide. Well, in any scientific experiment, you only want to change one thing and keep everything else consistent. So first off, we're all doing these at the same temperature. We don't even bother to mention that. We assume that's true. The other thing we do, in our first and third experiments, you notice that between those two, we doubled the concentration of fluorine, but we didn't do anything to the concentration of chlorine dioxide. And that's very important. If we want to find out what effect the concentration of fluorine has, we only want to change fluorine. And then in experiments 1 and 2, we see that between those two experiments, we kept the concentration of fluorine the same. And in this case, we quadrupled the concentration of chlorine dioxide. Now with each one of these experiments changing the concentration, it has some effect on the initial rate. So how do we find out what the orders of reaction are? Okay, well, let's take experiments 1 and 3. We know the generic rate law. We're going to use x and y for the unknown exponents for fluorine and chlorine dioxide. We're going to compare what happens to the rate in experiment 3 over what happens to the rate in experiment 1. We need to plug in all the information that we have. Now, we don't know what K is, but K should not change. The rate constant should be consistent throughout the entire experiment. And if we're comparing experiments 3 and 1, Well, we didn't actually change the concentration of chlorine dioxide. So the same concentration over each other, those are going to cancel out. Same goes for the rate constant. So we are left with this equation. Now we know what the rates, the initial rates of these reactions were, and we also know what the concentrations were for fluorine for those two reactions. We rewrite this, we put the exponent x outside, and then we plug in our information. Now we need to solve for that exponent. So when we doubled the concentration, we doubled the rate. And it should look pretty obvious that x is simply 1. Therefore, we have discovered what part of the rate law is. We now know that rate is equal to some constant k times the concentration of fluorine raised to the power of 1, which we don't show. We don't show explicit 1s in chemistry, times the concentration of chlorine dioxide raised to some power y. So, we need to go back to our first two experiments and solve for y. So this time, again, k should be constant. Fluorine was held constant. We didn't change the concentration, so we cancel those and ignore them. And now we have this. We plug in our information, and again, we see that when we quadruple the concentration of chlorine dioxide, we quadrupled the rate, while holding fluorine constant. Which again means that the order with respect to chlorine dioxide is also 1. And there is our rate law. So here's another example. Here we have a generic reaction. Our generic rate law, let's compare again experiments 3 and 1. Because in this case we held A constant and we doubled the concentration of B. We're going to plug in our information, and now we're going to solve for y. Now, it's not always obvious, and of course our data is perfect because this is a hypothetical situation, but now we can tell, y must be 2. And if you're not sure, use the law of logarithms. And you can solve for y by taking the natural log of 4 divided by the natural log of 2. So in this case, this was an order of reaction other than 1. And that's our experiment so far. Now, we have our rate law, but we still need to solve for x. So this time we're going to use experiments 2 and 1. Here we doubled A, but we kept B constant. And then of course we can ignore K. Now we're going to solve for x. And again, this one's pretty obvious, and if you do law of logarithms, it becomes even more obvious that x is 1 in this case. Now, we don't show the power of 1. That's implied. So this is the rate law for this generic reaction. But there's one more thing that we can do. We can solve for the rate constant at this temperature, whatever temperature that was that all of these experiments were run at. In order to do that, we need to take our complete rate law and we need to rearrange and solve for k. We're going to choose one of these experiments. It shouldn't vary that much, or we can do one calculation for each experiment and take the average. We're going to choose experiment 1. We're going to plug in that information. Don't forget to square the concentration of B, because that is based on our rate law. And we're just going to solve for k.